David Smith here with another Flip Classroom math lesson. 3 tips before we start. First, you can adjust the playback speed to suit your ability to consume the video. Second, you can pause the video at any point to catch up with your notes or jot down questions. Third, you can turn on the captions and read my words on the screen. Today's lesson is our first lesson in our probability distribution chapter. So, new concept, relates to probability, but we're going to take our basic understandings of probability from our last chapter and build on them in this concept of probability distributions. A random variable is a quantity whose value depends on the outcome of a probability experiment. Okay? So, for example, we're going to flip a coin 3 times. We take a look at all the possible outcomes, and X could equal the number of heads we get from flipping a coin 3 times. Let's look at that example. Flip a coin 3 times. Here is a list of our outcomes. Now, you know we could draw a tree. We could also make a grid for this. The random variable in this case is the number of heads we get when we flip the coin 3 times. Let's look at that example. So we're going to flip a coin 3 times. Here are our possible outcomes in a list. We get 3 heads. There's 3 ways we can get 2 heads. There's another 3 ways we can get 1 head. And then there's 1 way we can get 0 heads. So we actually have 4 different outcomes for this 3 coin flip problem. We can get 0 heads, 1 head, 2 heads, and 3 heads. So that's 4 outcomes. Let's look at some notation. So P capital X equals lowercase x. Now this might take a little getting used to because it's kind of confusing at first. The uppercase X is our random variable. This is the thing that we're looking for and we're going to talk about. So Px or X equals the random variable, which in this case is the number of heads that we get. The lowercase x is the actual number of heads in this experiment. So here is a question for you. P uppercase X equals 2. What this means is what is the probability in this situation of getting 2 heads? Pause the video and let's put that down here. Now this should be a pretty straightforward calculation based on what we've already covered in class. You can see that we have 3 places here where we get 2 heads. That's where the little case x is 2. So again, what this means is what is the probability of the number of heads in our experiment equaling 2? Uppercase x, that's the random variable. Lowercase is the outcome we're looking for. So I have 3 possibles out of 8 where I get 2 heads. So the probability is 3/8. All right, let's do a more complex example. So here it is. This uppercase X is the number of 6s in 3 dice rolls. So we're going to roll a die 3 times, and we're going to take a look at how many 6s we get. So here is what will become a familiar prompt. Tabulate the probability distribution for X. So tabulate is a key clue here that you're going to end up with a table that's going to show you the probability distribution. But before we get there, we need to also calculate our probabilities. So in this case, what I'm going to prompt you to do is make a probability tree. Now, remember, we've got 6 numbers on a die, but we're really only interested in either rolling a 6 or not rolling a 6. So don't make a tree with 6 branches at each event. Do it as just either 2 branches, 6 or no 6. So go ahead and pause the video, make a probability tree for rolling 6s in 3 rolls of a single die. Okay, in case you didn't know how to start, I'm going to start you. Here's my first roll. I roll the die 1 time. I have a 1/6 probability of getting my 6 and a 5/6 probability of not getting the 6. This is roll number 1. So if you haven't already done so, pause the video and finish this tree. We have 2 more rolls. All right, here's my tree. Now, I do understand that drawing these more complicated trees takes a little practice. I end up pretty crowded out here at the end with my 8 different branches. If you're not sure about the room, give yourself a lot of room on your page to make your tree. And the trick there is make that first branch pretty wide. That'll give you more room as you end up making all the other branches. Now take a look. I've put all my probabilities on my branches. In this case, we don't have no replacement. Every time we roll a 6, the odds are the same, or every time we roll the die. So these don't change because there's no, we don't have a problem where if you roll a 6, now there's no 6 on there. There's always the chance of getting a 6. Okay, so now I want you to pause the video and calculate the probability of each of these outcomes. Let's take a look at the results of that. Now what I've done here is I've tabulated my outcomes just to make it more clear. This top row is rolling 3 6s. This one is 2 6s and then no 6. This one is 6, no 6, 6. And so on. So this helps you understand what's going on the tree. Now calculating the probabilities with fractions, you just multiply the tops times the tops and the bottoms times the bottoms. So 3 6 is going to be just 1 over 216. And as you'll notice, all the probabilities are 216 because the bottoms of all these fractions are 6. 216 is just 6 times 6 times 6. So check this out. So now we get 6 6 no 6 is 5 out of 216. 6 no 6 is also 5 out of 216. And then finally 6 no no is 25 out of 216. Now if you look at this table, you can see the patterns involving the numerator of these fractions. So that's my tree with my probabilities calculated out. All right, so now what I would like you to do is summarize those results from the last board in a probability distribution table. Now let me talk to you about how that looks. Remember, lowercase x is the actual number of 6s that we got in our 3 rolls, and then uppercase X is the variable, which is the number of 6s. So what this table is asking you to do is saying for the lowercase x, what's the probability of getting none, of getting 1 6, 2 6s, or 3 6? So here's the notation. Probability uppercase x, that's the random variable, equals the lowercase x, which is the number here. So what you do is you look at your tree and you write in the probabilities for getting 0, 1, 2, and 3. So pause the video and do that. You're going to have a little bit of number crunching to do, but it's pretty straightforward. All right, so here's what I did. I got my 4 different probabilities to put in my distribution table. Now, I just want to review where these numbers came from. Remember, the tree had 8 outcomes. The 0, no 6s, that was just one branch at 125 over 216. So that got transferred over from the tree. Now, the ways to get 1 6, there were 3 of those. There were 3 ways, and they were at 25 over 216, each one of those 3. So we added those up to get 75 over 216 for rolling 1 6. Now, there were also 3 ways to roll 2 6s, but the odds of each one were less. So we had 3 ways at 5 over 216 each, which ended up giving us 15 over 216. And then lastly, there is only one way to get 3 6s, and that from the tree was directly 1 over 216. So that's how we got all of these probabilities from our tree. Now, let's ask some questions about the probability distribution. Let's talk about 2 things that are always true in a situation like this where you're looking at a probability distribution. So, first thing, in this situation where we have random variable x, lowercase x is the number of times that we actually got a 6, the probability, whatever you put in for lowercase x, it's going to be between 0 and 1. Whatever probability that is. And you'll notice on our table, it's definitely true. Okay, second thing, Greek letter sigma stands for sum. So what we're saying with this thing is that all the probabilities that are in our situation are going to add up to 1. So this is a fancy notation way of saying what I think you already know. And take a look at this one. If you add the tops, 125 plus 75, there's 200. Plus 15, there's 215, plus 1 more makes 216, which makes the sum of all 4 fractions equal to 1. Let's do a more abstract example with a probability distribution. So that last one was anchored in reality. We're actually calculating probabilities for a very specific situation. And all you needed to be told was it the situation, and you could analyze it and you could do that. You could create your distribution. Now this time, you're given a distribution that has no example. So what we've got here is we've got our little x. So the possible values of big X, which is our random variable, are 1, 2, 3, 4, and 5. Okay? So maybe it's a 5-sided die, maybe it's a spinner, maybe it's drawing things from a hat, who knows? But we do know that there are 5 outcomes, numbered 1 through 5. And then here's the more abstract part. The probability of the one outcome is 7C. The probability of the 2 outcome is 5C, 3 is 4C, 4 is 3C, and getting the 5 is just plain old C. So we don't actually know what these probabilities are. We're going to figure that out right now. So the first one, find what C is. Now you might be looking at that going, huh? How could I possibly do that? You can. One of these 2 rules will help you crack that code. So pause the video, think real hard, and see if you can figure out how to find C. So the trick is to realize you can use the sum condition that's always true. All of the probabilities will add up to 1 to solve for C. So what that means in our example is that this plus this plus this plus this plus that all adds up to 1. So that's the step I've written there. If you haven't already solved this, pause the video, solve that, come back when you find C. Pretty straightforward here. I'm just adding up all my C's. So I have 20C on this side equals 1. Divide through. So C is 1/20th. Here's a second example. I'm going to test your knowledge of the notation as a prompt to figure out what to do. So here we go. Probability that uppercase X is greater than or equal to 4. So pause the video, look at our information here, and do that calculation. So we know from our example that we need to have the outcome be greater than or equal to 4. So whatever this thing is, whatever this example is in reality, we're only interested in the 4 and the 5 as our little x, our lowercase x. So the probabilities of those, for the 4 we have a 3C, and for the 5 we have a C. So the probability that uppercase X is greater than 4 is going to be 3C plus C, which is 4C. And since we know that C is 1/20th, it's 4 times 1/20th, 5/20th, which is 1/4. One last thing. Now I want you to come back to this table, use what you've learned in the last 2 problems, and go ahead and fill out this table with the actual probabilities for each of these outcomes. Let's see how you did. 7C, C is 1/20th, so that's 7 over 20. 5C is 5 over 20, which reduces to 1/4. 4C reduces to 1/5. 3C is 3 over 20, and 1C, which we know from the very beginning, is 1/20th. Now that you've watched the video, jot down a few extra notes or questions for our next class. You can also re-watch portions of the video that didn't go in so well the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.